Ladies and gentlemen, colleagues, members of the public, it's lovely to see you all here this evening for this inaugural lecture. I'm Judith Squires and I'm the Pro-Vice-Chancellor for Education and Students here at the University of Bristol, and it's a great pleasure and privilege to be introducing this inaugural lecture. It's one of the joys of the job that I get to carry on learning about all sorts of things that I don't know about, and so this evening's lecture gives me another opportunity to extend my own learning, and I hope yours too. So this evening's talk is given to us by Professor Dan Lunt, who's Professor of Climate Science in the School of Geographical Sciences. Dan joined the School of Geographical Sciences at the University of Bristol in 2002 as a postdoctoral researcher. Much of Dan's work is driven by a desire to understand the world we live in and how it has varied in the past. To achieve this, he makes use of numerical models of past climates to test hypotheses derived from geological record. He also uses the past climate record to improve models and to better predict future climate change. Dan was contributing author to the most recent IPCC report, and he's founding chief executive editor of the Geoscientific Model Development, a journal designed for the description and evaluation of models of the Earth system. In 2010, he won the Philip Leverhulme Prize in recognition of the fundamental contribution his findings have made across a range of different subject areas. And in 2014, Dan was promoted to professor at the University of Bristol. And I'm sure that this evening's lecture will give you some sense of why we were so proud to be able to make him a professor here at the university. So without further ado, let me introduce you to Dan for this evening's lecture.
So, thank you very much. And so, in the talk today, I'm going to try and cover three different aspects of the work that I do. Two important aspects, and one that is a little bit more of a pastime and fun. So, the first of these is my work in trying to understand the past climate of our planet. And then, secondly, I'm going to talk about what we can learn from this, and actually not just what we can learn about that to do with the past, but what the implications of that are for our future climate. And then finally, I'm going to talk about something about fantasy climate change, and you'll see what that actually means in a minute. And I'm going to intersperse this with three different sort of sidetracks and diversions. The first of these is to talk a little bit about how I come to be here today, how I got to this point, some history. And then I'll talk about some of the people and things that have influenced me and inspired me on the way. And I'll finish off with some final words and summaries. And by the end of it, if you're still not sure what a climate scientist actually is, I will show you a little video that might explain it in a bit more detail. Okay, so you can wait for that at the end. Okay, so in terms of history, well, I went to school in Wimborne in Dorset and did A-levels in maths, physics, chemistry and French. You can see first day at school, bright-eyed and bushy-tailed, a bit more hair than I have now. But I think so when I was at school, really my best subject, the subject I enjoyed the most was maths. And actually that was partly because of some books actually that really quite inspired me. Oh, so before I say that, this was... By the end of my time at school, it looked slightly different. But so these couple of books that inspired me were, first of all, a book by Ian Stewart on the problems of mathematics, and also at home we were lucky enough to have a whole collection of the Time Life Science Library. I don't know if any of you people know that, but the mathematics book in that series was really inspiring, and really got me very interested in maths. So I thought about doing a maths degree at university, but for some reason I had it in my head that all mathematicians became accountants. So that combined with the fact that I also read this book, and this was the one that really inspired me actually to ultimately end up doing a physics degree at university, was this Strange Theory of Light and Matter by Richard Feynman, I just picked it up one day, started reading, and it was sort of a layman's introduction actually to quantum physics. And it had some examples in there, for example, of the way that electrons can behave both as particles and light and a wave, and a two-slit experiment. And it just really inspired me and sort of blew my mind that the world could work in this very unusual way. So I decided to learn more about that by doing physics at university. Actually, it turned out that physics at university was not like that at all. It was just solving equations, unfortunately. But so I was fortunate enough to go to Oxford to do physics, and as I'm sure you're aware, Oxford was a very beautiful place, but I think at the time I didn't entirely appreciate it, and spent most of my time playing cricket and football, which was very beautiful as well. But I did find some time to do some work as well, and in particular in my fourth year, I took some options in atmospheres, oceans, and planetary physics at the AOPP in Oxford, and this was one of the first things that really got me interested in climate science and meteorology and the weather and fluid dynamics. And so it was actually because of some of those lectures and some of the people who taught that course that actually led me ultimately to do a PhD at the end of my degree in meteorology at Reading. So Reading has got a very strong meteorology department. It's one of sort of the top places really in terms of climate science in the UK, not putting down Bristol at all, but it is a very good place to do, or there's some very good people there doing meteorology, and I did my PhD there on dust at the last glacial maximum in the present day. And so what I was doing was building a numerical model that represented and tried to understand desert dust and how dust was blown around the planet. And so I supervised during my PhD by Paul Valdez, who's here today and is at Bristol now, so I'll say more about him later. But at the time, one of the things that I found with this model was that there was some geological data at the time that said that there was a big increase in dust in the atmosphere during ice ages. And at the time, the sort of current thinking was that that was almost entirely due to the fact that when you have a cold ice age climate, you have more intensification of winds, and you get more dust into the atmosphere. But one of the things that we were able to show that actually that wasn't the reason, well, if you believe the model anyway, for that increase in dust, it was actually more to do with changes in vegetation and soil moisture. And so this was the first time I learned that really maybe the geologists could learn something from modelers, but I don't know if they would all agree. So Reading was, like I say, it was a very good place in terms of climate science, in terms of the training that I received while I was there. But actually, there was a very strong sort of work hard, play hard ethic at Reading. And one of the things that we did as a group of PhD students was we had an annual pantomime where we would all sort of dress up as members of staff at the time, or famous meteorologists. And for some reason, every year I ended up doing this in drag. I don't know why. So, for example, I played Mrs. L.F. Richardson, who's a famous, one of the first ever meteorologists. We had a talk here very recently from Professor Dame Julia Slingo, who's now head of the Met Office, who was also at Reading at the time, and I also actually played her in a panto. I didn't remind her of that when she came recently. And also the eminent meteorologist, Professor Sir Brian Hoskins. But actually the thing that I was most proud of during the time I was at Reading was we also had an annual croquet competition, which in the millennium year of the Golden Mallet croquet competition, I was the proud winner of the croquet competition. But anyway, after my PhD, I went abroad and worked. My first postdoc was at the LSCE in Paris in France, and this was the only photo I could find online of the building, so they're not particularly proud of it, so it's almost as bad as what we have in geography up the road, but not quite, no, I'm joking. Sort of. So this was where I worked. It was really good to work abroad for a while and be influenced by new people. One of the things, I was actually funded by the nuclear industry at the time, and they were interested in very long-term future climate predictions over timescales of sort of tens of thousands or hundreds of thousands of years in the future. And one of the things we did for this while I was there was actually make a prediction of what the world would look like without all the ice on Greenland. So if the Greenland ice sheet melted due to global warming in the future. And this was our prediction from the work that I did while I was then of the warming that you would get, actually, if the Greenland ice sheet completely melted. And surprisingly, to us at the time, we found that actually it's really, the warming that you get is quite localized. And in fact, if the Greenland ice sheet melted, in terms of the temperature effect that that would have more widely, wasn't actually as large as we expected. It was quite localized. So there were also, like I said, there were some people there who sort of influenced me at the time, and I enjoyed working with them. Two of them I'd just like to sort of mention and acknowledge: Gilles Ramstein and Yannick Doniger, who, although this was a while ago now, sort of 12, 13 years ago, these are people that I'm still working with now and sort of regularly collaborating with, which is very nice. So after that, I actually started, my second postdoc was when I came to Bristol for the first time. And I remember while I was still at France, we had a meeting in France that Paul was at the time, and we went out in the evening and were sort of reminiscing about the time while I did the PhD. And he said, "Oh, by the way, I've got this funding for a postdoc. Would you like to come back to Bristol with me?" And that was my job interview, and I said yes. And so I came to Bristol. And during this first postdoc, my second postdoc overall, first postdoc in Bristol, we worked on developing a new climate model, or Earth system model, that was called the Genie model. It was designed to simulate climate over very long timescales, so it was able to address questions about long-term past or future climate change. But really, this was sort of about model development. We weren't doing lots of experiments with the model, but trying to make it work better and test it and validate it. And one of the things I realized at this time, that there wasn't really a way that this sort of work could be published in the peer-reviewed literature very easily. Very often, the model for publication is that there are some people who spend a huge amount of time developing new models, and then other people come along and they run them and get all the glory, if you like. So we thought this is something we could do something about, and we actually founded this journal, Geoscientific Model Development, which was all about actually writing detailed descriptions of the numerical models, the computer models that are used for not only future climate prediction, but anything really about predicting anything about our Earth. And we started it about then, and it's still going. I've just resigned, actually. Just because of sort of time constraints. But it's been very enjoyable seeing that journal sort of grow and become useful for the whole community. So following that, I did another postdoc in Bristol, and actually this was when the sort of direction of my research changed, in that there was a project that came along that was really talking about understanding past climate over millions of years, looking at past climates on timescales longer than I've looked at before. It was this GeoSet project, again with Paul, and also Alan Hayward, who was then at the British Antarctic Survey. And this was, again, using numerical models to try and understand our past climate on long timescales. So, and that was 2005 to 2007. In 2007, I got a lectureship in the department here in geography in Bristol. And now, as of a few months ago, I guess I'm officially a climate scientist. So, what does this mean? Well, what I'm going to say really is a bit more about what I actually do, what it means to me. Rather than a climate scientist, I would probably really describe myself as a paleoclimate modeler. So someone who uses models, numerical models, to try and understand our past climate. And there are really two reasons why you would do this, or two reasons why I do it. And the first of these, like I said at the beginning, is, can we really understand our past climate? Can we understand the Earth that we live in and how it's varied in the past? But also, perhaps more societally relevant, what does this mean for the future? So I'm just going to say a little bit about these two. So first of all, can we understand past climates? Well, there are various different ways that we can do this. And first of all, you have geologists, earth scientists, who actually go out into the field, and they're sort of doing the real science, if you like. They go out and collect real data, geological data, to try and tell us something about how the climate of our planet has changed in the past. And then from this, they develop hypotheses or ideas about the reasons for that, the mechanisms that have caused climate to change. So that's something that I'm not particularly involved in. I'm more involved in this bit here, which is where we can then use models, which, as I'll say a bit more about what models actually are in a minute, but they represent in a sort of numerical form on a computer our best understanding of the Earth system and how it works. So, as I'll say in a minute, they include sort of all the equations of fluid dynamics, etc., that represent how our climate operates. And we can use these models to try and to set them up, if you like, to represent these past time periods, and we can use them and interrogate the models in a way that you can't always do with the geological data to actually really try and understand, if the model is correct, the reasons behind the changes in the geological record. So also, modeling can actually itself lead to new ideas and hypotheses about the way the world works, and which they themselves are then sort of testable by the collection by geologists of more data. And the models can also say the regions where perhaps you could most usefully or most productively go to collect more data. So really you can see that there's very much a sort of an interplay between the modelers and the data community. And this is something that I try and do, is sort of foster those links, if you like. It's not always easy because the geologists and the numerical modelers, if you like, sometimes speak a different language, or they have different aims and objectives, but that's something in particular that we're trying to do here in Bristol between the geography and the earth science department, is really bring together those two different communities. So the second thing is, how can actually this past climates go on to inform the future? Now again, one thing that I'm not going to talk a huge amount about, but what can be done is that past climate data on its own, again, as collected by geologists, can tell us something either contextual or qualitative or even sometimes quantitative about how, if you like, a forcing that we apply to the climate system, how much the climate system might respond, and that can have relevance for the future. But what we can also do, if we use models, we can actually use data that we've got, again, from the geological record to test our climate models. And very often, these are the same climate models that are used for predicting our own future. And so if we test them relative to past data, we can hopefully gain some confidence, or at least evaluate the models and see how good their future predictions might be by seeing how good their past predictions are. And then also another thing, and this is something I'll talk about a bit more in a minute, is sometimes geological data can actually help us model some aspects of the climate system more correctly, or model some aspects of the system that can't normally be modeled very easily. So these are some ways in which the past can inform the future, and in particular, in which past modeling of past climates can inform the future. So, what I'm going to do now is give you a couple of examples of how the work that I've done is actually done, and all the great people that I've worked with in the past have actually tried to address these two particular questions. But before that, I'm just going to talk briefly about some of the timescales that I'm going to talk about, because sometimes the numbers, when you talk about thousands, hundreds of thousands, millions of years, it's hard to get perhaps an appreciation of what those numbers actually mean. So I won't have many graphs, but this is one graph. And this was a very nice figure that was put together by Gavin Foster at the University of Southampton. And don't worry about worry about the data itself for the moment, but just first of all, in terms of the axes, this is actually what we call a log plot. And all that means is, as you go along the axes, basically, on the x-axis, we've got time, going back in time. The present day is here, just at the left of this bar that says future. And as we move to the left, actually time is going faster and faster and faster back in time. So effectively, if I move this at a steady speed, as we move over here, we're actually moving quite slowly through time, but as we get over here, we're moving very, very fast. And on the far left, over here, we've got 50 million years ago. Here we've got 1 million years ago, here we've got 1,000 years ago, and the present day here. And then you can see the CO2 numbers in terms of concentration in the atmosphere, in terms of parts per million, so the number of parts of carbon dioxide molecules in the atmosphere per million molecules altogether. So, like I said, present day here, 50 million years ago over here. But just again, to put some sort of context in this, I'm just going to put up some important events that happened over this timescale. So, 1966, we have England winning the World Cup. AD 250 comes about here, and I don't know how many of you have been to Lee Woods, but there's like an Iron Age camp, Stokely Camp in Lee Woods, and we think that was built just about here, in about AD 250. If we go back about 25,000 years ago is when the Neanderthals died out in a cave in Gibraltar somewhere. 800,000 years ago is here, and this is where the oldest evidence there is for stone tools in the UK, nearly 1 million years ago. If we go back 3 million years ago, that's here, we have the famous Lucy skeleton that was found in Africa, the Australopithecus afarensis, shown here, the Lucy skeleton about 3 million years ago. 65 million years ago, which is right at the very far end here, is where the dinosaurs died out. Okay. So what is the actual graph showing? Well, the graph is showing the concentration of carbon dioxide in the atmosphere over these 65 million years. And you can see a few things. So in fact, we can see the present day is here, and we can see that for the last, if you take 1,000 years ago, which is here, it's been since 1,000 years ago, or even going back here about 10,000 years ago, it's been fairly constant, the amount of carbon dioxide in the atmosphere. But then recently, just in the few decades or so, certainly the last 100 years, we've got a kick up, going from these background levels of about 300 parts per million to something today of about 400 parts per million. If we go further back in time, we begin to see some oscillations, and these are actually related to ice ages when this is relatively low. So we've got the last ice age here, about 20,000 years ago, where we had relatively low amounts of carbon dioxide in the atmosphere. But then as we go back onto timescales of millions of years, we see that we actually had CO2 relatively high about 50 million years ago here during what we call the Eocene period. What you can also see is that the recent increases in carbon dioxide over the last few decades to 100 years, this actually shows that you have to go back about 2 million years until you reach a time period in the past when carbon dioxide levels were as high as they are today. Another thing I'm going to do is just remove now this box which shows the current prediction or projections for how carbon dioxide in the atmosphere is going to change in the future. Now, we don't know exactly how it's going to change because we don't know how much fossil fuel we're going to burn, how much land use change we're going to do, but there are a range of different scenarios from the most recent IPCC report, the Intergovernmental Panel on Climate Change, and you can see that even under the sort of more optimistic type projections, you're having to go back tens of millions of years until we reach carbon dioxide levels similar to what we'd expect maybe by the end of this century. Okay, so that just puts a bit of context into perhaps a reason why we might be interested in some of these very warm climates of the past, or very high CO2 climates of the past. What did the world look like over these sorts of timescales? Well, I'm going to talk a little bit about 50 million years ago or 65 million years ago. You can see that plate tectonics on this timescale are having an effect on where the continents are. You can see that 65 million years ago, India, here, hopefully you can just about see at the back, was sort of in the middle of the Indian Ocean, yet to crash into the Eurasian continent and form the Tibetan Plateau and the Himalayan range. But when we're talking, actually I haven't got a figure of this, but 3 million years ago, which is the time period I'm going to talk about a bit more in a minute, actually the continents look pretty similar to what they do today. Okay, so that's a bit about how carbon dioxide has changed in the past. What about how climate has actually changed? Well, this is a record, so this is not a logarithmic plot anymore, so this is now a linear scale in terms of millions of years going back in the past. Again, the present day is here on the far right. These are millions of years, so 50 million years ago is about here. 60 million years ago here. And here we've got the global average temperature at the time as derived from the geological record. I'm not going to go into detail about how that's actually done, but that will be sort of a whole lecture in itself. But basically, this is an estimate from the geological record of how temperature has varied over this timescale. And you can see that in these very high CO2 warm worlds about 50 million years ago is also very warm. And in fact, compared to the present day, where the global mean temperature is about 14 or 15 degrees C, you're talking about a world where the average temperature of the world is maybe 25 or more degrees C. So a huge increase in the global average temperature. We also know that these very warm worlds are associated with these times in past Earth's history when the amount of carbon dioxide in the atmosphere was similar to what we might expect at the end of the century. You've got a very, very different world from the world we live in today. So, for example, there's evidence from Antarctica, which at this time was still situated over the South Pole, of flowering plants and leaves, monkey puzzle trees on Antarctica. This is an artist's impression based on geological data of what the Antarctic Peninsula would have looked like during these very high CO2 warm climates. of this greenhouse world. So this gives you, this is a way in which the geological record can provide some context to what might happen in the future. But actually what I'm going to talk about mostly today is this part of the record here. So in the last 3 million years or so, where you've got this gradual cooling trend, and what I should say is actually we don't know why we have completely still in paleoclimate science, why we have this gradual cooling, and in particular, we don't know why. We think it's most likely linked to the CO2 decrease over the same time, but we really don't know why CO2 is changing over these timescales. Or we know what the most important mechanisms are, but we don't know really what the balance between them, whether it's changes in emissions or changes in weathering that are really driving these changes in carbon dioxide. But there's this gradual cooling, and towards the end of this record, over the last 5 million years or so, 3 million years, we've had an enhancement of the amount of glaciation in the northern hemisphere. So the world's got cooler, and we've ended up with more ice in the northern hemisphere, as well as more ice in Antarctica. So what are the reasons for this? Well, I think I'll skip over some of this for the interest of time. But this is a piece of work I carried out in 2008, so about 6 years ago, and we were interested in this part of the geological record, this enhancement, this cooling of the planet, and this enhancement of glaciation over Greenland. And actually, at the time, there were 4 main hypotheses out there from the geological record about why glaciation had enhanced at this time. One of them was because at this time, North and South America are actually coming together in terms of plate tectonics, and prior to this time, there was an open seaway between the Atlantic and the Pacific. And at this time, when this glaciation enhanced and we started getting ice on Greenland, was the same time as these 2 continents were coming together and the seaway was closing. And it was thought that this closure of the seaway would actually increase the amount of ocean circulation and bring warmer waters from the equatorial regions towards the high latitudes of the Arctic up here, and that warmer water would lead to more evaporation of moisture into the atmosphere and therefore lead to more rainfall, snowfall, and allow the buildup of ice on Antarctica. So that was one hypothesis. Another one, that it's also a time when actually tectonic changes are occurring in North America, and the Rocky Mountains in particular are beginning to grow and expand and increase in height. And it was thought that that change in height of the Rockies could change the atmospheric circulation and actually lead to colder air masses arriving over the Greenland continent and leading again to a cooling. So a totally different mechanism. There was another mechanism out there that was related, again, to changes in the ocean, and there was an idea that during these warm climates 3 million years ago, prior to this glaciation, actually the ocean could exist in a state that where it was almost like a permanent El Niño event. So an El Niño event in the present day is just an event that lasts a few months to a year, and the tropics become relatively warm, and there are various changes around the whole Earth system, in fact. And one of those changes is that actually North America, and eastern North America, and in particular over Greenland, actually is warmer. But then the idea was that 3 million years ago, we sort of switched from this permanent El Niño to something more similar to what we had today, and that therefore caused a cooling over Greenland, and therefore an increase in ice and glaciation. A final hypothesis that really there wasn't a huge amount of evidence out there. This is some data that was around at the time for showing how carbon dioxide on this axis was changing over, well, it hasn't got an x-axis. If an undergraduate showed this graph, they would get 0 mark. But this is 3 million years ago here, and the present day here. And really, the CO2 data, the carbon dioxide data from the geological record was all over the place. But we thought maybe what if there was a decrease in carbon dioxide at that time in the atmosphere? That would also cause a cooling, an enhancement of glaciation. So all those hypotheses were out there. From the geological record, it's very difficult to say which of those might be the most important, but that's where we came along with a numerical model. So what is a climate model? Well, I'll just go over this briefly. This is a schematic actually of the model that we used at the time. You can see that it divides the world up in the atmosphere and the ocean into a number of what we call grid boxes. And actually the model can't tell you anything about what's happening on a scale sort of smaller than one of those grid boxes. Now, numerical models these days, numerical models of the climate system, are a much higher resolution than the one I show here. But at the time, for the sort of experiments we were doing, this was sort of a fairly typical resolution. And it represents, according to our sort of fundamental understanding of fluid dynamics of the atmosphere and ocean, including these sort of very fundamental physical concepts, it simulates the climate of our system, basically from first principles. You have to take into account some sort of sub-grid scale processes that are going on at a scale smaller than one of these grid boxes. But essentially, that's what the model did. And with a model, you can almost sort of play God, and you can make changes to the model in any way you want. And so we set up the model for these different hypotheses. Like we tried opening the Panama Seaway, we tried raising the Rocky Mountains, we tried switching from this permanent El Nino state to a normal state of the ocean, and we tried decreasing the amount of carbon dioxide in the atmosphere. And this is what happened. In terms of over Greenland, where we were interested in terms of the temperature change that we saw when we made these 4 different changes, and the rainfall change, so in red is showing there was a warming, blue is showing there was a cooling, blue down here is showing it's getting wetter, red down here shows it's getting drier. So, for example, you could look at the CO2 hypothesis and say, well, yeah, it's getting colder. The model is agreeing with that hypothesis and says it's getting colder. That's great. But you could also look at this one and say, yeah, the Panama hypothesis, we're also agreeing with that because it's getting wetter, and therefore you get more snow and build-up of ice. So this is where we realized that actually just using a climate model wasn't enough, and we had to also use an ice sheet model, a model actually of the Greenland ice sheet, to try and see actually which of these changes were actually significant in terms of the change in ice. And we did that, and this was the result that we found. And actually we found that if you closing the Panama Seaway, changing the state of the oceans, the El Nino, raising the mountains, all did almost nothing to the total volume of ice over Greenland. And actually only the change in carbon dioxide was able to lead to an expansion of the Greenland ice sheet to something more similar to what we see today. And so basically our conclusion was that although we didn't have much geological evidence to support that at the time, that probably a decrease in carbon dioxide was the most likely reason for that expansion of ice. Following that, actually there was some work done by Rich Pankos, Gavin Foster, Danny Schmidt, and others, Simon Secchi, in Bristol, who actually found some evidence from the geological record, and you can see from their paper here, you've got 3 million years ago here, present day over here, and they showed that actually from evidence from ocean sediments and looking at, I won't go into detail of how they did it, but essentially they found that indeed when they looked at higher resolution that had been looked at before, there was some evidence for a decrease in carbon dioxide in the atmosphere. So that was, very nice that that was sort of vindicated in some way, or that idea was vindicated by the geological record. And following this, actually we had some funding from who was the Dean of Science at the time for basically a meeting to bring together the whole international community to try and get more detailed and better records than these initial ones and the previous records that existed. That was a very fun and, I think, successful meeting. We then got some follow-up meeting funded by the Royal Society to discuss these ideas further, and actually building from that, ultimately, for several of us, that's what led to our involvement in the most recent IPCC report. So I think the reason I sort of showed that is because it shows that just something that originally starts off and you've no idea what's going to happen can actually have, big knock-on effects later on, much later on down the line, like a decade on in this case. So I'm going to have to start speeding up quite rapidly. But so just to say that now this sort of work is continuing on. We're now trying to look over even longer timescales, and actually, we've actually got, there are a couple of postdocs that I've got at the moment working on this, Alex Farnsworth and Claire Lopsom, who are basically trying to set up our model over a much longer timescales. These animations go over 160 million years, and they set up our climate model for all these different time periods, and are looking at how the climate system, this graph here is showing the temperature over the oceans through this time, how the changing continents and changing carbon dioxide and the relative role of those two, what role they play in actually in controlling the climate of our past Earth. Okay, so I thought I would have a bit of a break now and talk about some of the people and things that have influenced and inspired me over the years. And first of all, I'd like to just say a huge thanks to my parents. They both know, and they've given us a huge amount of support, both myself and our family over the years, and that's hugely appreciated. One thing that in particular I remember when I was a child at school, we had to produce a sort of science project every term or so. This was when I was at middle school, so aged, oh God, whatever that was, 12, 13-ish. And they gave me a huge amount of support actually at home in actually doing these science projects and, not giving me the answer, obviously, but, inspiring, teaching me how to think, basically, and how to think like a scientist. And actually my first, in one of these projects was sort of my first foray into climate science where, well, I say I built it, I think Dad probably had more of a role in building it, but actually we built a thermometer in the garage made out of one of his beer brewing demijohns, or wine brewing demijohns with a big tube stuck out the top. It was graduated in degrees Lunt, which the fixed points were 0 degrees, which was the heat of the garage, temperature of the garage, and 77 degrees Lunt, which was the top of the tube. So that was my first sort of foray into climate research. I'd also like to acknowledge my brother George, who has remained a hugely good friend over the years, and fortunately we still get on. Unfortunately, we're still both Rotherham fans, so that's not so good. But, okay, so that's my parents and brother. Also, someone else who's been hugely influential to me is Paul Valdez. I mentioned him earlier as being my PhD supervisor and postdoc supervisor, but I was just sort of thinking of some words that sort of described him. He's always been hugely inspirational. His enthusiasm is infectious. He's also hugely entertaining. He's extremely knowledgeable. He reads a huge amount. I don't know how he has the time to do that. He's technically brilliant. He's sort of developed and maintained almost the entire modelling infrastructure that we have for the climate group in Bristol. He's extremely hard-working, and also he's very nurturing. He's always, I think, been hugely good to me in terms of the development of my career, and I know that's the case for others in terms of, bringing them through and looking after them. So I also found this picture of him. It's, I had another picture, but I didn't want to show that. But anyway, you can ask me later. So also, and I thought something that probably still holds now, this was actually from the acknowledgements from my PhD thesis, where I said I'd like to thank him for providing many an entertaining and interesting discussion and enabling me to attend several sunny conferences, and I think that still sort of holds now. So, also some other people who I've been fortunate enough to work with over the years, and most of them, I think these are the people probably I've worked most with and sort of been inspired by the most, if you like, over the years. So Alan Hayward at Leeds have done a lot of work on the Pliocene time period that I talked about in terms of the Greenland work. Andy Ridgewell, who've done quite a lot of work on geoengineering that I haven't talked about today, but is a whole other aspect to some of the work that we've done that basically started, as most conversations with Andy do, sort of in the pub or over coffee or whatever. And he just said there was something in the New Scientist about how people were considering using mirrors in space to try and modify a future climate. And Andy said, oh, well, you could model that, couldn't you? And so we did, and that started a whole stream of research that we did in geography. Also, Rich Pancost, who's, again, like Paul, his enthusiasm is hugely infectious, and he really is does inspire you to be excited about the science you do. And also Gavin Foster, who was at Bristol, now down at Southampton, again, who's someone who just has these ideas that are sort of totally crazy, but then a few years later you find actually that I think it was Andy who once said that he knew it was going to be a good day when he got an email from Gavin one morning that said the title was something like Volcanoes, Miocene, Rats, or something like that. I don't know what it was, but it was like he has these crazy ideas that often actually end up being true. Also, people who've influenced me, actually all the people that I've been fortunate enough to work with, either my PhD students or postdocs, all who are listed. So one of my most recent ones, Alan Kennedy, I couldn't find a photo of, so I put his namesake up here, the 70s, 80s Liverpool footballer. But yeah, all of them have been hugely exciting to work with. They've been inspiring to me, and also hugely fun to work with as well. So also, I especially like to highlight Emma Stone, actually, because she was my second PhD student, but one of my earliest PhD students, and she's been with me basically all the time that I've been, pretty much all the time I've been through here at Bristol, either as a PhD student or as a postdoc, and she's now doing some really exciting work actually with the Met Office. So Okay, so there's some influence, but also, of course, I would like to recognise and thank my wonderful and amazing family for always being there for me, and especially to my, well, not especially, sorry, all of the three of you, but to my wife, Emma. You know, being an academic, there is a huge amount of travel that is involved with being an academic. So, you know, I do go to all these Sunday conferences and things, but basically the bottom line, that means that Emma is at home with the children and basically doing the real hard work at home. So that is, I would like to hugely thank her for all her love and support over all these years, and also, of course, to Ollie and Evie, who are unfortunately for them, having to sit through me talking here. But so here you can't see the photos here, or we can't see them there. Here they are in their most recent school photos. Okay, so that was another little diagram. I really am going to have to speed up here. So if we're going to get onto the fantasy climate change bit. So the next bit I wanted to talk about was about how the past can inform the future. And I thought I'd give a couple of very quick, I'll go quickly through the first one. And that is to do with this concept of climate sensitivity. So climate sensitivity is a measure of how much the climate system will warm up if you double the amount of carbon dioxide in the atmosphere. The IPCC says it's in the range 2 to about 4.5 degrees if you double the amount of carbon dioxide in the atmosphere. Now, this is a useful number because given a certain carbon dioxide change that we might think might happen in the future, you can estimate what the temperature change and other impacts to the climate system are going to be. But also, given a temperature change that you might not want to exceed, for example, the 2 degrees C target of the European Union, you can work out, if you know this number, how much carbon dioxide that means you can end up with safely in the atmosphere. However, it turns out, this was about 4 years ago we worked on this, it turns out that this is mainly something that's a number that you try and get at with climate models. But it turns out that actually a lot of these models were ignoring some important processes that we know from the paleoclimate record are actually important. And in particular, they tend to ignore what we call feedbacks or changes to the climate system that occur when you increase the amount of carbon dioxide in the atmosphere that tend to occur on very long timescales. So things like resulting changes in vegetation or ice sheets like Greenland and Antarctica. And so what we thought was maybe we could go back in time to a world when CO2 was relatively high and try and investigate how changes in vegetation and ice sheets actually amplified that climate change and therefore might mean that maybe we were underestimating climate sensitivity. And we actually found a time period, and actually it was the same time period that I was talking about earlier, the mid-Pliocene, 3 million years ago. And actually it turns out there's some geological data from, for example, pollen records that have been trapped in ancient lakes or what have you that can tell us something about what the vegetation was like at the time. We also have sea level records that can tell us how much ice was in the climate system. And we were able to put these changes into our model. So what we did, we started off with our model just going along simulating sort of a pre-industrial type climate, and then we did 2 experiments. One where we just increased carbon dioxide, did like a traditional climate sensitivity type experiment, looked at how temperature increased. Then we did another experiment where we included these extra effects that looked at how vegetation and ice sheets might amplify those feedbacks by putting in these past climate representations into the model based on geological data of how the ice would shrink. You can see that there's less ice on Antarctica here than we have here, and less ice on Greenland here than we have here in this warm Pliocene world 3 million years ago in the present day. So when we did a sort of a traditional climate sensitivity type experiment, we found the world warmed by about 3 degrees in our model, which was that very close to the central traditional estimate. However, when we included these extra feedbacks, we got more warming because of the vegetation and ice sheet changes, and actually we got about 50% extra warming, and we called this sort of extra warming or this extra warm state of the climate system, rather than the climate sensitivity, we called it the Earth system sensitivity. So, and that work came out actually just before the Copenhagen COP conference, the Climate of the Parties, and actually I think well, I don't have any evidence for this, but there were certainly some people there who knew about this work at the time, so that was quite rewarding, if you like. So I think I'm going to skip over this next bit, because it's not quite as interesting, and in the interests of time. But basically what I was saying here is that also this other aspect that we can use the past climate to evaluate our climate models and see how good they are. And here we've got an estimate of the future climate state in terms of temperature. Here's the scale down here of the future. And then the same model, or same ensemble of models, group of models, used to predict 4 different past climates. And then what the dots show is what the geological record says the past climate, the temperature change actually was. And you can see that in all these 3 cases, 3 very different climates, actually the model is doing a reasonable job of getting the magnitude of that temperature change in agreement with the geological record. So that gives us some sort of qualitative confidence that our models are doing something at least vaguely sensible. And like I said earlier, this is something that Emma Stone is now, but the question is, when we do this comparison, does that actually change the way that models are developed? Does this feed back into, for example, the UK Metofis who write these models? And the answer and if I look back 3 months ago, I would say definitely not. That's never really happened in the past. But very recently, we've just started working actually directly with the Metofis, and this is something that Emma Stone is leading, is to try and actually feed back some of these comparisons into the Metofis as they develop their most recent version of their climate model. And so we're hoping that these past climates will actually materially influence our future climate predictions. Okay, so to move on to the last section, as well as this, I am also a keen Tolkien fan. This is the top left of our bookcase at home, and you can see these are all the Tolkien books that I have on my bookcase. I have also been known to dress up as Radagast or Gandalf or what have you. Now, an obvious way of sort of combining my interests in climate and Tolkien was actually to carry out a simulation of Tolkien's worlds that he invented, the Middle-earth. And actually, we were just around the time I was thinking about this, me and Rich and a few others were actually writing a proposal to NERC. So NERC, the Natural Environment Research Council, the body that give out money to UK scientists to carry out research. Now, as part of these proposals, we have to submit what we call an impact plan, which is something about how we're going to, not about the science we're going to do, but how we're going to communicate this science, or how we're going to engage with industry or the general public or whatever to make our science into something useful, if you like. And we thought that actually we could put this into the impact plan for one of our proposals. So this is actually part of the impact plan that we put in. We said that we were going to do this, and the reason we said there's a perception that climate models are heavily tuned to the modern day. And so that's sort of an argument that you hear sometimes from climate skeptics. And we believe that by doing this, you'll actually highlight the flexibility of climate models and show that they're not necessarily tuned to just simulate the present day or even our own world. And we also said we didn't request any funding for this work, which we said I'd do in our spare time. Now, we actually get some reviews for these, and these were generally positive. They said, very exciting, Middle-earth sounds fun, it leverages public fascination with the fictional universe. We also got some that weren't quite so positive. They said, not convinced this is really viable or wise, little constrained, what lies along the map. I can see this backfiring. The press could run this story about public-funded scientists modeling fantasy world. But anyway, it got funded, so they must have ignored this one. So what do we do? Well, first of all, we have to set up the climate model to simulate this time period. This was sort of the map that we had to go by, which is what J.R. Tolkien drew. Most of his stories took place in this part of the world called Middle-earth, but he did actually draw this picture of the whole globe, which we then converted by sort of tracing this and then converting it into something the computer could read. We generated a map that the computer could use in the climate model, and it's exactly the same process that we use, well, apart from the tracing bit and all this, but this bit was exactly the same process that we use when you simulate past climates. So we set this up, we ran the model, and miraculously it worked, I think, 3rd time. It needs a little bit of jiggling about. And here are the results shown for over the region of Middle-earth, where most of Tolkien, so here's like Mordor, where Sauron lives. Here's the Shire. Has anyone not read the books or seen the film? Okay. So most of the Hobbit action sort of takes place up here. But this is the global, this is the temperature that our model predicted in the region of Middle-earth. And here's kind compared to the present day. And you can see, as you'd expect, we put in to the model that the actual, Tolkien's world was actually a sphere. And so because of that, you end up with, as you'd expect, colder regions towards the Earth, where there's less per unit area of the Earth, there's less insulation from the sun that Middle-earth or the Earth is receiving. So that's why both the real Earth and Middle-earth both get colder as you go towards the pole and warmer as you go towards the equatorial regions. It also is colder over the mountainous regions. These sort of black lines you can see here are the mountains, and the real world, as well as Middle-earth, as predicted by the model, get colder. And all these things aren't things that aren't things that we tell the model. They're things that actually emerge from the fundamental equations of fluid dynamics that are from our sort of fundamental understanding. Model also predicts rainfall, again here for the present day compared to Middle-earth. And again, you see some interesting things, like, for example, you get a lot of rainfall over, for example, the Misty Mountains here and over Mordor, but you get a rain shadow just to the east of these mountainous regions. That explains, for example, why the trees that the dwarves and the Hobbit hid in caught fire so easily when the goblins came and tried to burn them down, because they were just here in this very dry part in the east of the Misty Mountains. Actually, Tolkien said that in the books. So he was actually, he knew something about meteorology. Okay, so we found, Mordor was very, very dry, actually. I actually gave this talk at not the whole talk, but this bit of the talk at it was called Bristol Con, and it was sort of a convention all about fantasy worlds. And I gave this talk, someone said, oh no, this must be wrong, because it says that they grew crops in Mordor to keep to feed all the goblins and people, but I think it must have been sort of they must have had some irrigation down from the mountains. But then also the model predicts sort of more obscure things like the pressure patterns and the wind fields, and you see things like the model it just produces these from the fluid dynamics. They're not things that are sort of programmed into the model per se, but you get things like westerly winds in the mid-latitudes, and you get easterly winds at the higher latitudes here, and actually this might explain why they set off from here in the Grey Havens when the elves go and sail off to the west, because that's where the prevailing winds were at the time. So also the model predicts things like vegetation, and actually this just sort of gives a flavour of the fact that what I was showing here was sort of averages over many, many years or for a particular season, but as the model's running, it's actually sort of stepping forward in time at a sort of an hourly time step. And this actually, you can make things like this, which is an animation of the rainfall in Middle-earth as we go through time. And each step of an animation is, I think, 6 hours or something. And you can see that the model is spontaneously producing frontal systems, rain belts that are moving across through the prevailing winds from the west to the east, getting trapped in some cases by the topographic mountains. And so and all, like I said before, all these things are emerging from the fluid dynamics. Another bit of sort of fun that we had with this was because we were interested in maybe, where in Middle-earth or where on our Earth is like various parts of Middle-earth. So we looked, for example, first of all, the Shire, where Bilbo Baggins set off from. The red regions are where both where the temperature and precipitation in our Middle-earth simulation for where the Shire is matches where it is in our Earth. So basically, in this red region here, in the UK, is the most Shire-like region. Turns out it's sort of Leicestershire, apparently. And in New Zealand, it's in the South Island just here. And actually, they filmed the film in the North Island, so they got that wrong, definitely. But also, you can look at, for example, on Earth, where is Mordor? And it turns out I was delighted when I saw this, because basically, you find out that Los Angeles has the climate almost exactly of Mordor. Also, we found, for example, various parts in Australia, which was very nice, because we were, at the time, England were playing the Ashes down under at the time, and we thought, and in fact, as this work came out, I think they were just playing in Adelaide, which was just, actually, I don't know really where that is, but somewhere down here. Okay. But also Alice Springs here in the middle. So as we're academics, we like to publish things. We published this in a paper called The Climate of Middle-earth by Radagasta Brown. We also published it in Dwarvish and Elvish. thanks to Greg Tort, our technician, our computer support person in Bridge, who actually translated these for me. In fact, he did it only take. I won't give a secret away, but did these very nice translations. So, and again, so to sort of draw a parallel with some of our past climate work, if this was a simulation of the past, you'd be interested in, well, is there any data from the geological record that we can use to say whether these simulations are any good or not? Well, there obviously isn't really in this case, but I did get an email from a geologist from Australia just after this came out, who said he'd spent his whole life doing field work actually just around Alice Springs. And it turns out, where we said Mordor was, and it turns out that there is actually a geological feature called Mordor Pound, just 70 kilometers northeast of Alice Springs. So that is like proxy paleogeological data, agreeing with our simulations. Okay, so we got some nice and interesting comments about this on various websites when it came out, so it was all a bit of good fun. But I think it was useful in sort of communicating with the general public about a bit about climate modeling and how climate models work, and their strengths and weaknesses. So I'd just like to finish off with a few things that sort of, I guess they're useful things that I've learned over the years about, things that have helped me really. And I think I would sort of summarize these with these 4 things. Work hard, there's no sort of substitute for that, but also don't work too hard and play hard as well. Take opportunities when they come. I mean, that is been, I think for me that's been incredibly important in that some of these don't come off sometimes and some of them don't go anywhere, but by taking those opportunities, if you don't take those opportunities, then you never know and you never get the chance. Also, an important one, I think, be prepared to change your mind. There are some people who I think get really sort of wedded to a hypothesis or an idea, and even in the face of sort of mounting evidence against it, they will sort of fight it to the death because maybe they sort of built their early career on some of those ideas. But I think sometimes it's really important just to take a step back and say, well, I'm not necessarily wedded to that particular idea, and take on sort of new evidence as it comes. And also this one, to collaborate, don't compete. Again, I think in the modeling community, that does very much happen. There's really a culture of sort of sharing and working together and collaborating, but I think that isn't always the case in all other communities that I see, where there's much more sort of culture of competition and not necessarily sharing results and things. So I think wherever possible, collaborate and don't compete. So, I think I'll put this video on at the end as people are leaving. If you're still not sure what a climate scientist is, then I'll leave that playing. But thank you very much for listening.
So Judith has asked me to just quickly bring things to a close. As most of you know, we don't have questions at the end of inaugural lectures, but there will be wine in the back. So you have a choice of wine, conversation with Dan, and a bit of lingering around and watching the video that he's going to put on in a few moments. However, I just want to thank Dan for a fantastic talk that illustrates exactly why you were promoted to professor, and in terms of the depth, the breadth, but also the real sense of joy and fun that you have in the work that you do. And as someone who's worked with you, but even before I worked with you, I think, and on behalf of many people across the university, we're equally inspired by all the ideas and enthusiasm you have. I just wanted to say two specific reflections. The journal you founded, you commented about that was an absolutely vital resource to acknowledge the people that have developed the models, but also, it is a fantastic exercise in transparency by making those models available and having conversation around them. And that is something, as an institution, quite proud of what you've achieved there. A little bit of a lighter note, Dan was really enthusiastic about that Middle-earth modeling. And he started that as soon as the grant was funded. And probably finished it before the postdoc was even appointed. I'm not sure what the track record is for delivery of impact plans, but I can assure you Dan is probably the only person in the entire UK funded by any research council who delivered the impact plan before the project actually even started. So, well done. Thank you so much. I'll leave you with one last quote associated with the Middle Earth that I think sums it up all very well, which was that, I forget what blog started this, but said, "One does not simply model the climate of Mordor unless you're Dan Lunt." Congratulations, thanks for being an inspiration, and thanks for a fantastic talk. Cheers, Dan.